Hello everyone, my name is Feng. I'm from Huazhong University of Science and Technology in China. It's my honor to be here to present my paper, Fire, Combining Multi-Stage Filtering with Taint Analysis for Scalable Recreating Vulnerability Detection. With the development of software open sourcing, reusing software becomes common. Synopsys reported in their OSSRA that 96% of codebase contain open source, 84% contain at least one known open source vulnerability. This results in an increasing number of recurring vulnerabilities. These vulnerabilities exhibit similar characteristics, share code logic, or may even be identical, so they are also known as clone vulnerabilities. Among existing recurring vulnerability detection tools, Wenjie supports large-scale scanning. However, it cannot detect recurring vulnerabilities with syntactic changes and doesn't consider patch information. To address this, Wenjie detects syntactic recurring vulnerabilities by adding the oldest version of vulnerability and patch information. However, the time overhead remains high. In general, they either fail to detect recurring vulnerabilities with syntactic changes, do not consider patch information, or have high time overhead. So there is a current need for a method that can enable rapid detection for very large-scale recurring vulnerabilities, support for detecting vulnerabilities that make a syntactically different but semantically identical change. Consider the difference between vulnerability and patch. Our paper makes the following contributions. We propose a scalable recurring vulnerability detection method based on multi-stage filtering and differential taint paths. We implement a prototype system called Fire for effective and scalable detection of recurring vulnerabilities in open source software. We conduct an in-depth comparative evaluation of Fire against other two state-of-art methods. The results demonstrate that Fire can achieve large-scale vulnerability scanning with high precision and recall. Then we introduce the system design of our paper. Fire comprises two phases, filtering phase and the vulnerability identification phase. The filtering phase improves efficiency by reducing the number of candidate functions. The vulnerability identification phase improves the effectiveness by distinguishing between vulnerabilities and patches through tainted paths with semantic information. In this part, we focus on introducing the filtering phase, which consists of three stages: bloom filter, token filter, and ST filter. Each filtering stage significantly reduces the number of functions to be inspected in the subsequent stage, greatly speeding up our method. To filter recurring vulnerabilities, we use crucial features to create feature vectors instead of the full code. We extract 177 important features from each code fragment, grouped into 4 categories. We then create an 177 dimension feature vector for each function. If a feature is present, its position in the vector is set to 1. We use a bloom filter for the first stage of filtering. A standard bloom filter has h-hash functions and an m-bit array to present the set as. Each bit in the array is either 0 or 1. Here is how it works. The first, initialization. Start with an m-bit array of all zeros. Then insertion. For an element A1, apply h-hash functions to get h-hash values and set the corresponding bit in the array to 1. Final query to check if an element B1 is in the set, apply h-hash functions, get h-hash values, and see if all the bits at this position are 1. If yes, B1 is in the set. If no, it isn't. Standard bloom filter can only check for exact matches, so they cannot handle functions that are only slightly different. For example, A2 and B2 are similar, but B2 cannot be queried if A2 is in the set. To detect a wider range of vulnerabilities, we create a shuffle fuzzy bloom filter for approximate queries to find similar vulnerabilities. The new bloom filter adds the operations of shuffling and discarding. For A2, the insertion phase will shuffle 1, 2, 3, 4, 5 into 5, 4, 3, 1, 2, and discard the first element to get A'2. The query phase will also shuffle B2, 1, 2, 3, 4, 6 to 6, 4, 3, 1, 2, and discard the first element to get B'2. Since A2 and B2 discard the only different element, A'2 and B'2 are exactly the same. Therefore, the shuffle fuzzy bloom filter can query B2, which is implemented to support the querying of slightly modified functions. At the second filtering stage, we extracted the tokens of functions to consider the lexical information. First, we pass the function and extract token sets. Then we calculate the similarity score between the token sets of the function and the vulnerability by using Jacquard similarity. Finally, we return the functions with high similarity scores and all their corresponding similar vulnerabilities. In the final filtering stage, we introduce patch information to check the syntactic similarity between target function, vulnerable function, and patch functions. Before performing the syntactic similarity analysis, we first perform line-level filtering based on two conditions. Then we measure the similarity by calculating the number of nodes shared between two STs, and the target function must satisfy the following conditions. The vulnerability identification phase involves signature extraction and vulnerability detection. We use Taint analysis to extract signatures. For example, we consider the function that contains 3 variables in the figure. Size and buffer are used by 2 different functions, so we can extract 3 tuples. Then we analyze a propagation of each tuple. For example, variable size appears in the condition statement of an if statement and is then used by the malloc function. That is the first Taint propagation path in the figure. After extracting all Taint propagation paths, we replace each node in the path with the corresponding complete code line. These Taint paths constitute the signature of the function. We do the same for vulnerabilities and patches, and we extract the differing parts, considering paths that are unique to vulnerability as vulnerability signatures, and paths that are unique to patches as patch signatures. We extract vector representations for all paths. Each path is represented by a vector, and each function is represented by a set of vectors. We match each function vector from the target function with all path vectors from the vulnerability function, keeping the highest similarity score for each path. If the target function has n paths, we end up with n highest similarity scores as 1 to Sn. Averaging these scores gives the final similarity score S between the target function and the vulnerable function. We identify vulnerabilities by checking if the target function's signature matches the vulnerability signature but not the patch signature. To examine the capability of FIRE on detecting recurring vulnerability, we conduct several evaluations. Evaluations include 4 parts: dataset and matrix, detection effectiveness, detection efficiency, and the significance of multi-stage filters. For the collection of our vulnerability dataset, we use PatchDB and manually collecting vulnerabilities. For target system, we select 10 popular C and C++ open source projects that cover various application domains from the open source community. We use the widely used metrics to measure the performance of FAIR. In our paper, we compare FAIR with two accurate and scalable tools for detecting recurring vulnerabilities, Wenjie and Maury. From the table, we can see that FAIR outperforms Wenjie and Maury in detecting recurring vulnerabilities. For example, FAIR achieves a detection precision of 90% with a recall of 77.4%. Both Wenjie and Maury are inferior to FAIR. The time overhead of each tool is recorded in the figure. Wenjie has the least detection time because it doesn't consider any semantic information functions compared to Maury, which also considers data flow and control flow information. Our detection speed is faster. This indicates that FAIR can scale to large software projects, meeting practical needs in real-world application. With the second row of the table, we can see that the number of functions returned after each filter significantly decreases, indicating that each filter we set up plays a role. We propose and implement a novel method named FAIR. FAIR can rapidly detect extensive recurring vulnerabilities through multi-stage filtering. Support for detecting complex recurring vulnerabilities with syntactic changes, and consider difference between vulnerabilities and paths by using differential taint paths. Our evaluation results demonstrate that FAIR outperforms state-of-art methods for recurring vulnerability detection. Thanks for your listening.